Let's begin with a limit as n approaches infinity of n to the 1 over n. So if I were to look at each n individually, what I would get is infinity over 1 over infinity. And this is an indeterminate form, so obviously I'm going to have to find a different approach. The key to solving this problem is to rewrite n to the 1 over n as e to the ln of n to the 1 over n power. The reason I'm going to do this is because, well, first, if I have something like e to the ln of x, this is x, because I'm composing two functions that are inverses of each other. So whenever I compose two functions, I just get x. And it doesn't matter the order of the inverses, obviously. So e and natural log are inverses of each other, so when I compose them, they cancel, and I get whatever is in the parentheses here. So now I'll be looking at the limit as n approaches infinity of e to the ln of n to the 1 over n. One of the properties of a log is to bring the exponent in front. So let's say I have ln of x squared. This is the same thing as bringing the 2 in front and multiplying it by ln of x. So the exponent here is 1 over n, and we're going to pull that in front of the natural log. So this will just be limit as n approaches infinity, e to the 1 over n times ln of n. Okay. And I'm going to rewrite this. So this step is really optional, but just to make it look nicer, it's ln over n. And as n approaches infinity, we know that natural log of x looks something like this, and so it approaches infinity, and so does n. So that's a good sign, right? We have infinity over infinity, so it makes sense to use L'Hopital's rule eventually. But the problem is I have e to the infinity over infinity. That is not the form I want. I want to have only infinity over infinity. So I need to get rid of this e. And what I'm going to do is I'm going to bring the e down, and then I'm going to put the limit as part of the exponent. So it'll be the limit as n approaches infinity of natural log n over n. Now, the limit is infinity over infinity. So I'm going to apply L'Hopital's rule. So the derivative of ln of n is 1 over n. The derivative of n is just 1. And now the limit part is just 0. So this whole thing is 0. So it's e to the 0, which is 1. Okay, so my limit as n approaches infinity of n to the 1 over n is just 1. So the next problem, we'll be looking at a similar problem, but we're going to change the parentheses, what goes inside the parentheses. So I'm going to have a plus n. So a is just some constant. We're going to raise that to some exponent p over n. Here p is also a constant. Okay, so a and p are some constants. Okay, the approach is the same. I'm going to use e to the natural log and rewrite this thing. The exponent is p to the n, and we know that the exponent goes in front of the log. So I'm going to rewrite it like this. So p and n, and I'm really going to ignore the p for now, and I'm going to focus on the ln of a plus n over n. So that's going to give me infinity over infinity. And multiplying by p doesn't really change anything. So I'm going to get rid of the e by putting it on the bottom. And then now we're going to do limit as n approaches infinity, p of ln of a plus n over n. Now, my limit is infinity over infinity. So that's good. I can use L'Hopital's rule. So I'm going to take the derivative of the top and the derivative of the bottom. The derivative of the bottom is just 1, so I'm just going to ignore that. And then the derivative of the top is p over a plus n. Clearly, the limit goes to 0, so this will be e to the 0, which is 1. So my limit, as n approaches infinity, of a plus n to the p over n is 1.